All right, so buckle up, everyone, because today we are taking a deep dive into the cosmic mysteries of dark matter and dark energy.
Sounds exciting.
You bet it is.
I like it. An ambitious goal, but I think we can do it.
Oh, yeah, I'm feeling confident already, and trust me, there's some wild stuff ahead. We're talking about things like a galaxy made almost entirely of dark matter, and even some possible connection between dark matter and black holes.
It really makes you question how much we actually know about the universe, doesn't it?
Absolutely. Like right off the bat, the sources all hit us with this idea of the 5% problem.
Right, the 5% problem.
Which basically means that everything we can see out there, all the stars and planets and galaxies, all that jazz, it only makes up a tiny fraction of what's actually out there.
It's a humbling realization, isn't it? All the stuff that we've spent millennia studying and trying to understand.
Yeah, like all the stuff that we can actually see is just the tip of the iceberg.
Exactly. The vast majority of the universe, something like 95%, is made up of stuff that we can't even see.
Dark matter and dark energy. So, okay, let's start with dark matter, which is often described as this sort of invisible scaffolding holding the universe together. Would you say that's a good way to think about it?
I think that's a pretty good analogy. It's called dark because it doesn't interact with light, so we can't see it directly.
Right, it's invisible.
But we know it's there because of the gravitational effects. We can see how it influences the way galaxies move and how light bends around massive objects.
So, like, we can't see it, but we can see what it does.
Exactly.
That's so cool. So one of the key pieces of evidence for dark matter came from Vera Rubin's work on galaxy rotation curves, right?
That's right. She was studying the way that stars move within galaxies, and she found that stars at the edge of galaxies were moving way faster than they should be.
Based on just the stuff we can see.
Exactly. It's as if there's this unseen mass surrounding each galaxy, providing the extra gravitational pull needed to keep those stars from flying off into space.
So there has to be something there, even though we can't see it.
Precisely.
And it's not just galaxy rotation either. Gravitational lensing also provides evidence for dark matter, right?
Yes, that's right. Einstein's theory of general relativity tells us that massive objects can actually bend the path of light.
Like a cosmic magnifying glass.
Exactly. And when we observe distant galaxies, we sometimes see their light being distorted or even multiplied as if it's passed by some invisible mass.
And that invisible mass is dark matter.
That's the leading explanation. Those gravitational lensing effects are difficult to explain without the presence of a significant amount of unseen matter.
So we have all this evidence pointing to the existence of dark matter, but the big question is, what is it actually made of?
Yeah, that's a million-dollar question. The sources we've got here talk about some pretty exotic possibilities, like things called WIMPs, axions, and sterile neutrinos.
It sounds like something straight out of Star Trek.
It does a bit, doesn't it?
So what are these things, these WIMPs, for example?
Well, WIMP stands for weakly interacting massive particles, and they are a hypothetical type of particle that could make up dark matter. They're thought to be much heavier than the particles that make up ordinary matter, but they interact very weakly with it.
So they're kind of like loners of the particle world.
In a way, yes.
I love it. What about axions? I've heard they are incredibly light, almost like ghostly particles.
It's a good description. Axions were originally proposed to solve a problem in particle physics, but they also happen to have properties that make them a good candidate for dark matter.
And sterile neutrinos, those are even weirder, right? They don't even interact with the weak force like regular neutrinos do.
Exactly. They're hypothetical particles that are thought to interact only through gravity, making them even more difficult to detect than regular neutrinos, which are already notoriously hard to find.
Wow, so we've got these heavy WIMPs, these ghostly axions, and these super shy sterile neutrinos, all as potential candidates for dark matter.
And the thing is, each of these possibilities has its own strengths and weaknesses, and scientists are still trying to figure out which one, if any, is the correct answer.
It's like a giant cosmic puzzle.
It really is.
So we're talking about all these hypothetical particles and trying to figure out what dark matter is made of, but then we have this galaxy called Dragonfly 44.
Ah, yes, Dragonfly 44.
Which seems to be made almost entirely of dark matter.
It does. It has a similar mass to our Milky Way galaxy, but far fewer stars, which suggests that the vast majority of its mass must be in the form of dark matter.
That's incredible. What does that tell us about the variety and strangeness of the universe?
It's a reminder that we still have so much to learn. It suggests that there might be a whole spectrum of galaxy types out there, some dominated by dark matter, others, surprisingly, seem to lack it entirely.
Wait, galaxies with almost no dark matter?
It seems counterintuitive, doesn't it? But recent observations suggest that there might be galaxies out there that have very little if any, dark matter.
So maybe there are multiple forms of dark matter, or maybe our understanding of gravity needs some tweaking.
Those are possibilities that scientists are actively exploring. These discoveries challenge our assumptions and force us to reconsider our models of the universe.
It's also fascinating, and we haven't even touched on dark energy yet.
We've only just scratched the surface. Dark energy is perhaps even more mysterious than dark matter, and it has profound implications for the fate of the universe.
Okay, so before we dive into the weird world of dark energy, are there any key takeaways about dark matter that our listeners should keep in mind?
I think the most important thing to remember is that dark matter isn't just some abstract concept. It's all around us. It permeates the universe, and its gravitational influence is shaping galaxies and clusters of galaxies.
So even though we can't see it, it's playing a huge role in the universe.
A huge role. And the search for its true nature is one of the most exciting and challenging quests in modern science.
Absolutely. This has been mind-blowing so far.
And we're just getting started.
All right, so stay tuned, everyone, because in part 2, we're going to tackle the enigma of dark energy.
Buckle up.
Okay, so we've covered dark matter, this invisible stuff holding the universe together. But now we're moving on to dark energy, which seems to be pushing everything apart.
Yeah, and at an accelerating rate, no less.
I know, my mind is already kind of blown here.
It's a concept that really challenges our intuition about how the universe works.
Right, like for the longest time, astronomers thought that the expansion of the universe was slowing down due to gravity.
Makes sense. Gravity pulls things together.
Yeah, so what's with this whole pushing things apart thing?
Well, that's where dark energy comes in, you see. Back in the late 1990s, 2 independent teams of astronomers were studying these distant supernovae, and they stumbled upon something totally unexpected.
Oh, and these supernovae, they're like those exploding stars, right?
Yeah, they're incredibly bright. So bright, in fact, that we can see them from billions of light years away.
Like cosmic beacons.
Exactly. And because they explode with a very specific brightness, we can use them as standard candles to measure distances in the universe.
So what did they find?
They found that these distant supernovae were fainter than they should have been, meaning they were farther away than expected.
Oh, so the universe was expanding faster than we thought.
Much faster. The expansion wasn't slowing down, it was speeding up.
Whoa, so it's not just expanding, it's like hitting the gas pedal.
That's a good way to put it. And to explain this accelerated expansion, we need something more than just matter and gravity. We need something that pushes everything apart.
Enter dark energy.
Precisely. Dark energy is the name given to this mysterious force that seems to permeate all of space, acting as a sort of anti-gravity pushing everything apart.
Wow, and this isn't just based on these supernovae, right? Our sources mention other evidence for dark energy, like something called baryon acoustic oscillations.
You're right. Baryon acoustic oscillations are another important piece of the puzzle. They're kind of like ripples in the fabric of space-time.
Ripples.
Yeah, you see, in the early universe, just after the Big Bang, there were these tiny fluctuations in density, little ripples in the otherwise smooth sea of matter and energy.
Okay, I can picture that.
And these ripples, they propagated outwards as sound waves, just like ripples on a pond.
Sound waves through the early universe, that's amazing.
And as the universe expanded, these sound waves, they left an imprint on the distribution of matter.
So we can still see the effects of these ancient sound waves today.
Exactly. By studying the distribution of galaxies, we can see these patterns, these baryon acoustic oscillations. And these patterns tell us a lot about the history of the universe's expansion.
And they confirm that the expansion is accelerating.
Yes, the size and spacing of these oscillations are consistent with a universe that is dominated by dark energy.
Okay, so we've got exploding stars and ancient sound waves, both pointing to dark energy. But what is dark energy actually?
That's the billion-dollar question we still don't know for sure. But there are some leading theories.
All right, let's hear them.
One possibility is something called the cosmological constant, which was actually first proposed by Einstein.
Einstein, really?
He originally introduced it into his equations to describe a static universe, one that wasn't expanding or contracting.
But then we discovered that the universe is expanding.
And Einstein famously called the cosmological constant his biggest blunder.
But now it's back in the spotlight.
It is. You see, the cosmological constant represents a constant energy density that permeates all of space.
Like a built-in anti-gravity force.
A good way to think about it. And this constant energy could be driving the accelerated expansion of the universe.
So dark energy could be a fundamental property of space-time itself.
That's one possibility, but there are other theories too, like something called quintessence.
Quintessence. Sounds fancy.
Quintessence proposes that dark energy isn't constant, but rather it's a dynamic energy field that can change over time.
So instead of a constant push, it's more like a push that can vary in strength.
Exactly. And depending on how this quintessence field evolves, the expansion of the universe could speed up even more, or maybe even slow down or reverse in the future.
So the fate of the universe hangs in the balance, kind of exciting, kind of terrifying.
A little bit of both, I suppose.
And there's even more radical ideas out there, right? Like the idea that maybe our understanding of gravity needs some tweaking.
That's right. Some physicists believe that maybe Einstein's theory of general relativity, which describes gravity, might need to be modified on very large scales.
Maybe gravity doesn't work exactly the way we think it does when we're talking about the entire universe.
Precisely. Those are some of the questions that cosmologists are grappling with right now.
It's all so mind-boggling. So our sources say that dark energy makes up about 68% of the total energy content of the universe.
A huge chunk.
If we don't even know what it is, how can we possibly hope to understand the universe as a whole?
It's a daunting challenge, but it's what makes studying dark energy so compelling. It's a reminder that we're still at the frontier of knowledge, pushing the boundaries of what we understand about the cosmos.
It's kind of humbling, isn't it?
Absolutely. And every new discovery brings us closer to unraveling these mysteries.
So this has been a deep dive into the theory, but I'm also curious about the practical side of things. How are scientists actually studying and measuring dark energy? What tools are they using to probe this elusive force?
That's a great question, and it's something we'll explore in Part 3. We'll dive into the cutting-edge experiments and missions that are on the front lines of this cosmic detective work.
Okay, I can't wait, so stay tuned, everyone, because in Part 3, we're going to get into the nitty-gritty of how scientists are trying to pin down dark energy.
Could be fun.
Okay, so we've really gone deep into the theory behind dark matter and dark energy, but now I want to know, how are scientists actually trying to get a handle on this stuff?
Well, it's really a multi-pronged approach, using some of the most amazing technology we have, both on Earth and in space.
Like, give me an example. What kind of technology are we talking about?
Well, for starters, there's the Large Hadron Collider, or the LHC.
Yeah, the LHC, that's the one where they smash particles together at super high speeds, right?
Exactly. It's basically the world's most powerful microscope. It's this massive underground tunnel where they accelerate protons to nearly the speed of light and then smash them together.
And the idea is that, these collisions could create new particles that might give us clues about dark matter.
Exactly. One of the leading theories is that dark matter is made up of these things called WIMPs, weakly interacting massive particles.
Right, those super heavy particles that hardly interact with normal matter.
And the hope is that by smashing protons together at such high energies, we might be able to create WIMPs and actually detect them.
That would be a huge breakthrough, wouldn't it?
It would be revolutionary. It would confirm the existence of a whole new class of particles and give us a much deeper understanding of what dark matter really is.
Okay, so that's one approach, but I know we're also looking for dark matter from space, right?
Absolutely. There are a number of space-based experiments that are searching for clues.
Like the alpha magnetic spectrometer, the AMS?
Right, the AMS that's mounted on the International Space Station, it's constantly scanning the sky for cosmic rays.
Cosmic rays.
Yes, those are high-energy particles that come from outer space. Some of them are produced by exploding stars, others by distant galaxies, and it's possible that some of them are produced by the annihilation or decay of dark matter particles.
So the AMS is basically looking for a needle in a cosmic haystack.
In a way, yes, but it's a very sophisticated needle detector. It can measure the energy and charge of these cosmic rays with incredible precision.
And it's already found some interesting things, right? Like that excess of positrons?
You're right. The AMS has detected more positrons than expected, which could be a sign of dark matter annihilation. But there are other possible explanations as well, so scientists are still trying to figure out exactly what's going on.
It's like a cosmic detective story.
It really is.
Then you have those underground experiments like Exion on T and LUX.
Ah, yes, the underground experiments.
These are the ones that are buried deep underground to shield them from background radiation, right?
Exactly. They're trying to directly detect dark matter particles, specifically WINKs.
And how do they do that?
Well, imagine these massive tanks filled with liquid xenon, buried far below the Earth's surface.
Okay, I'm picturing it.
The idea is that if a WIMP happens to pass through the detector and collide with a xenon atom, it will produce a tiny flash of light that can be picked up by sensitive detectors.
So they're waiting for these little bursts of light that could signal a dark matter interaction.
Exactly. And these experiments are incredibly sensitive. They're pushing the limits of our ability to detect the faintest interactions.
It's amazing. It's like they're trying to hear a whisper in a hurricane.
That's a good analogy.
Yeah.
And then there's the IceCube Neutrino Observatory.
Oh, yeah, that's the one buried in the ice in Antarctica, right?
That's right. IceCube is a truly unique experiment. It's a cubic kilometer of ice instrumented with thousands of light sensors.
And they're using all that ice to detect neutrinos.
Exactly. Neutrinos are these subatomic particles that are incredibly difficult to detect. They can pass through almost anything.
Ghosts of the particle world.
A good way to put it. But when a neutrino does interact with matter, it can produce a flash of light. And that's what IceCube is designed to detect.
So they're looking for these flashes of light deep under the ice.
Precisely. And IceCube is particularly interesting because it's searching for evidence of sterile neutrinos.
Those super elusive neutrinos that only interact through gravity.
If sterile neutrinos exist, IceCube has a good chance of finding them.
Wow, this is a lot of different approaches, but it sounds like they're all focused on dark matter. What about dark energy?
Well, studying dark energy is a bit trickier because it doesn't interact with matter directly, but we can still learn a lot by studying its effects on the expansion of the universe.
So how do we do that?
One way is through large-scale surveys of galaxies, like the Dark Energy Survey and the upcoming Euclid Mission.
So these surveys are mapping the distribution of galaxies across the universe.
Exactly. By measuring the distances and redshifts of millions of galaxies, we can create a 3D map of the universe and track how its expansion has changed over time.
And that tells us about dark energy.
It does. The way that galaxies cluster together and the rate at which the universe is expanding are both influenced by the amount of dark energy in the universe.
So by studying these large-scale structures, we can indirectly measure the properties of dark energy.
Precisely. And then there are space telescopes like the Fermi Gamma Ray Space Telescope.
Fermi, that's the one that observes the universe in gamma rays, right?
That's right. Gamma rays are the highest energy form of light. And Fermi is scanning the sky for gamma ray signals that could be produced by dark matter annihilation or decay.
So it's another way of trying to detect dark matter.
And it's also helping us to map the distribution of dark matter in the universe.
So we've got all these amazing experiments and missions all working together to try to unlock the secrets of dark matter and dark energy. It's incredible.
It's a testament to human curiosity and our desire to understand the universe.
It really makes you realize how much we still don't know.
And that's what makes it so exciting. There's so much more to discover.
You've definitely given me a lot to think about. Like, you know how we were talking about dark matter being spread out in this web-like structure throughout the universe?
Yeah, the cosmic web.
Well, I was wondering, could the filaments of this web be somehow connected to the supermassive black holes that we find at the centers of galaxies?
That's a fascinating question, and one that scientists are actively investigating. There's some evidence to suggest that there might be a connection, but more research is needed.
Well, I'm definitely going to be keeping an eye out for any new discoveries in this area. This has been an incredible journey through the cosmos. Thanks for taking us on this deep dive.
My pleasure. Keep exploring the universe. There's always something new to learn.